Okay, so we've done the intro on thermochemistry, heat, and heat transfer and types of calorimeters. Now we need to talk about one more term and do some math problems, and that is specific heat. And we've established the fact that in every physical and chemical change, energy is always transferred. And we measure that energy transfer by a temperature change. And there's going to be three things that can influence how much heat is transferred. The first is the type of material. And if you think about this, this is why we select certain materials as insulators or not based on how much energy they let pass through. Obviously, if something is tougher for energy to pass through, it might make a good insulator, where something that's really not great at holding energy is not going to be a good insulator. The second thing is the mass. Okay, if you have more of something, the energy is going to have to pass through more of it. So, the mass of material, as well as the size of the temperature change. Okay, again, if we think about, weather, because that's familiar to us. If you walk outside in, the middle of January and it's -4 degrees outside, well, you're going to lose a lot of energy really fast. That's why you may have on several layers of material. That would increase the mass of your energy to travel through. And you may pick the type of material. You may pick a good insulating material in order to keep you warm. And that leads us to what's called specific heat. And specific heat, which is abbreviated with a C, is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius or Kelvin. Celsius and Kelvin, again, have the same increments, so they're kind of interchangeable for this particular term. But if I had 1 gram of a substance, I need to figure out how much energy it would take to raise the temperature of that 1 gram by 1 degree Celsius or Kelvin. Okay? And since you see some numbers in there, we're going to do some math. Okay, now for specific heat problems, they're usually measured under constant pressure, which we abbreviate as C with the subscript of a P, which is the specific heat measured at constant pressure. It's not a huge factor right now, but it is how it's measured. Okay, now the equation, there's going to be two equations, and you're going to get both of these. The first one, and I'm going to tell you what they mean here in a second. You've got Cp equals Q over M times delta T, and the other option is Q equals Cp times M times delta T. And you will be given both versions of this equation to choose from. Now, Cp, like we said, is going to be the specific heat at constant pressure, and the units for this are either going to be joules over grams times Kelvin, or joules over, actually there should be a G in there, joules over grams times Celsius. And I'll show you where that comes from. Q is heat, which we talked about earlier. It's going to be measured in either joules or kilojoules, so there's the conversion that we mentioned. M is mass, which is grams, which hopefully at this point we've got drilled into our head. Forgot a parentheses there. And lastly, you have delta T. The delta symbol refers to change, and whenever you measure the change in something, and we talked about this earlier with heat transfer, it's always temperature final minus temperature initial. That way, if you have a positive delta T, it means that the temperature increased from start to finish. If you have a negative delta T, it means that your temperature decreased. Okay, and that's going to be very important, because when we get to heat, all right, if something it's going to directly impact this, because you can't have negative mass that we know of, and you don't have negative specific heat. So the other thing that may happen is that our Q values, if you have a negative value for Q, it's going to be exothermic, and if you have a positive value for Q, it's going to be endothermic. Okay, so the signs are important here, so trust yourself. A negative answer doesn't mean you're wrong. Alright, so let's do some samples. The first one says a 4.0 gram sample of glass was heated from 274 Kelvin to 314 Kelvin and was found to absorb 32 joules of energy. What is the specific heat of the glass sample? Okay, like all math problems, the first thing that we got to do is list out our known and our unknown. Now, it's a really good idea, and some of us have gotten away from this, that when you write the known numbers, put the units, because it's going to help you figure out what they go with. Okay, 4.0 grams. Well, that's going to be my mass. Okay, so mass is 4.0 grams. It says heated from, let me get this out of the way here, and this is glass up here, that's where that comes from. But anyway, heated from, so temperature initial is going to be 274 Kelvin. Wow, how about that? Let me flip that around again. 274 Kelvin. Temperature final is going to be 314 Kelvin. And it was found to absorb 32 joules of energy. And remember, that's going to be Q equals 32 joules. And we are looking for the specific heat, which is going to be a constant pressure. Okay, now I'm going to do the actual math problem on the next slide, but before I go any further, I do have to figure out my change in temperature. I can do that ahead of time. So again, my delta T is temperature final minus temperature initial. So if I take, and I'm going to set this up the old-fashioned way just to show you here, 314 minus 274 is going to give me a final answer of 40, but I have to put a decimal place because of significant figures. So there's two significant figures. There's also two significant figures in my mass and two significant figures in my heat. So that means that my answer can only have two significant figures. So let's set this up. Alright, I'm looking for specific heat. So the version of the equation that I'm going to choose is this one. I'm going to put Cp is equal to Q over mass times delta T. That X is just a time sign. Alright, so I'm looking for Cp. I'm going to put the units in here to show you where we get the units in our answer. We have 32 joules over 4.0 grams. There's a point there. Okay. Times our delta T, which was 40 with a decimal place, and we're dealing with Kelvin. And again, just as a reminder, it doesn't matter if this is Kelvin or Celsius, it doesn't change the values, but that's what we can use. Now, oops, I do need to manipulate this equation and solve for it. I'm going to go ahead and solve for the bottom first, just to make my life a little bit easier. And if I take 4.0 times 40, that's going to get me to 160 grams times kelvins, because I have to keep those units. So now I got to take 32, divide it by 160. Remember, my final answer can only have two decimal places. So for my Cp, specific heat, it's going to be 0.20, and my units are joules over grams times Kelvin. And that's my final answer with two sig figs and a unit. And remember, that comes from the fact that I had joules up here and then grams times Kelvin. Nothing cancels out, so I got to keep all of it. Okay? Alright, next one. This one says, how much energy will the same glass sample gain when heated from 314 Kelvin to 344 Kelvin? Now, on appearance, it doesn't look like it gave us much information, or enough that what we need, but what we have to do is pull some of the old information. If it's the same glass sample, that means that the mass is still going to be equal to 4.0 grams. Now, we also just found the specific heat of that sample, which is 0.20 joules over grams times Kelvin. All right, and that's the thing with some of these problems, is you have to think about it and be able to pull information you find in one step and use it in another step. Now I'm going to go ahead and do my delta T up here. So I'm going to take 344, which is my final temp, minus 314, which is my initial temp. That's going to get me a temperature change here of 30 Kelvin. Okay, so last problem, we had a temperature change of 40 Kelvin. Now we only have a temperature change of 30 Kelvin. So if I just make a quick prediction, that should mean that the energy will be a little bit less. So let's see if that's correct. Alright, so I'm going to put my delta T, which is going to be, again, a positive 30 Kelvin. I'm not putting the positive sign, but it can be negative. And I'm looking for the Q. Okay, so this time I'm going to pick Q equals Cp times the mass times the delta T. Okay, and I've just got to plug and chug here. So my Q, and I'm going to put the units to show you how they cancel out. I've got 0.20 joules over grams times Kelvin. Come on. There we go. Times 4.0 grams. So that's going to get rid of the gram unit. Okay, and then I'm going to have times 30 Kelvin. And that's going to get rid of the Kelvin. Actually, I should probably use parentheses here so that we're not lost on what we're doing math-wise. Okay, now this is simply plug and chug. I got to take 0.20, multiply it by 4.0, and then take that and multiply it by 30. Okay, two significant figures again in all my data, so two significant figures in my answer. So Q is going to be equal to 24 joules. Okay, and so if I backtrack and just look at my comparison, to raise this same sample of glass, 30 Kelvin, it only took 24 joules. And if I look back to the answer on my last slide, I was the temperature had been raised from 314 to 274 when it required 32 joules. So the temperature change is again reflective and directly related to how much energy needs to transfer.